Okay, so again, this is the subject, the topic we're on, and we're on 1A.1 function relationships, and we're on page 1 of our interactive notebook, and we're drawing this into a page 1. Yes? Okay. Once you're done drawing, give me a thumbs up so we can go ahead and get the show on the road to fill in. So what we're going to do together is we're going to define what a linear function is and identify the characteristics. What you're going to do at your table is come up with examples and non-examples of it based on the definition and characteristics. Does that make sense? Okay, so we do the top together, the bottom you do collaboratively at your table. All right, so I haven't written on this thing all summer, so please bear with me. I will get better at my handwriting, but it's going to be questionable for a minute. Okay, so the definition that we're going to use when we're talking about a linear function, it is going to be a relationship between two quantities, and those two quantities, as of right now, we're going to call them X and Y, with we're going to write this capital, constant rate of change. Okay. With okay, that didn't get better. That got worse. With a constant rate of change. Okay. Now, constant rate of change. You guys learn this as meaning the what? And what does that represent? There you go. Your constant rate of change is the long way of saying slope. But we're big kids now, so we understand that that's our constant rate of change. All right, the characteristics of a linear function that you should have left Algebra 1 knowing is that it can be written in multiple forms. So you should have left with the first form we're going to talk about, and that is going to be our slope-intercept form. Slope-intercept. And slope-intercept form is our y equals mx plus b. Does that ring a bell? Okay. Your slope-intercept means that from this, you should be able to tell me what the slope is, which is your m, and you should be able to tell me what your y-intercept, which is your b. Okay. Your y-intercept is 0, comma, whatever the b value is. That's your y-intercept. That's the number one thing you should have left Algebra 1 knowing. Agree? Okay, number 2 is going to be our standard form. So standard form, that is ax plus by equals c. Okay, in standard form, it's telling you simply the two relationships have an output, right? From here, you can isolate y, you can still solve for your y-intercept, you can do all those things, but this is it in standard form. All right, the next thing is that your point slope form, which probably was the least used of the forms. So you have point slope, and point slope is y minus y1 equals m times x minus x1. It literally means that you've been given a point and the slope, and then from there you can create the equation. Okay? Yes. And then the last characteristics of a linear function is graphically. Graphically, it is simply a non-vertical line. That is what a linear function is, a non-vertical line. All right, so in the examples box, you're going to create a graph example. So you're going to create some kind of graph for me and create an equation of your choice. So create a graph and equation that represents a linear function based on what you know the definition is and the characteristics are. All right, so let's see. So again, a graph just has to be anything that is a non-vertical line, right? A line that is a line, but it can be whatever your heart made. I'm gonna do you. There's a graphical representation. Is it vertical? No. Okay. Your equation can be whatever you want it to be. My equation is gonna be my kids' birthdays. February plus August equals 21. Okay. That's all that means, that you understand that I can take these characteristics and I can reiterate them into something and manipulate, because there's infinite possibilities for your examples. Does that make sense? Okay. Your non-examples. For your non-examples, I want you to think about any of the things that you did not sort on Friday into the linear pile. So what is a non-example of a linear function? So think about things that are non-examples. Your non-example may be different than the person next to you, but what is a non-example of a linear function? I can't even accept that. That's just terrible. No, what did you call them? Yeah. All right. So here are my non-examples. So my non-examples, I drew a vertical line because a vertical line is not a linear function. Okay. It's a linear relationship, but not a linear function. I drew a parabola because a parabola is curves. All right. So that's linear. So, does that make sense? Okay. Now, we're now going to go into page 2. On page 2, you're going to draw a Frayer model, but this time it's going to be for quadratic functions because they're their own entity. We're learning to identify things that we couldn't fill out on our post-it notes. There's a lot of talking, so that means we're ready to go on. Let's learn about quadratic functions. So the number one thing that I saw on your little post-it notes that you guys knew was the quadratic formula, which I don't know if you know how to use it, but I saw that you guys knew the quadratic formula. The quadratic formula is used with the quadratic function, but it is not the quadratic function, okay? It is a part of it that helps us find our zeros or our non-real zeros. So let's talk about what is the quadratic function. So your quadratic function, it's again, because it's a function, that means it's a relationship between two things, right? So we're going to always start off with a relationship between two quantities. So it's a relationship between two quantities. If y'all ever wonder why Miss Jones may type things out, it's because she really struggles with writing. I don't know why. And those quantities are going to typically be x and y, but x and y are interchangeable because depending on the real world problem, x has its own variable representation and y has its own, right? So the difference here is it is with a, and this time we have a linear rate of change. I wanted it to be capitalized, but then I stopped capitalizing. Don't know why. That is terrible. What is going on? Linear rate of change. Okay, so it's a linear rate of change, which means that to get from one number to the next, you are multiplying by something and then adding something. I didn't mean to write an X, I meant to write an N. Don't write the X, don't write the X, write the N. Okay. So to get from one to the next, you're multiplying by something, that number by something, and then adding something. N stands for number, and that's what the difference is. That's how you're getting from one number to the next, one number to the next when you have a quadratic relation. Okay. For quadratic, again, reiterating what a linear rate means. This is a B. Yeah, it's a B. Please, you will not hurt my feelings if you ask me when I write something. I write like a questionable toddler. I don't know. Right. First, we're gonna talk about the shape of a quadratic. When you're graphing a quadratic, the graph, anyone knows what it's called? What is the graph called for a quadratic? Starts with a P. A parabola. If you want to spell it, it's parabola. I know. It's the disease of math. Parabola. Okay. Your parabola, not parabola, your parabola is either going to be positive or negative. A positive, yeah, right. Your positive parabola is a smiling, happy parabola. Your negative parabola is a sad, frowning parabola. When you have a positive parabola, you're going to have a minimum value. And when you have a negative parabola, you're going to have a max value. All right. Questions about the graph of a quadratic. If the graph doesn't look like this, is it a quadratic? No. Okay. Next, what does it look like in terms of an equation? So we have our standard form. And standard form, that's going to be y equals ax squared plus bx plus c. That's our standard form for a quadratic. You may not have the last two terms, the bx and the c, as this is the primary term that lets you know that it is a quadratic. Notice here that the power is a 2. Okay, if your highest power on your variable is a 2, then it is a quadratic. Okay, our next form is called vertex. So vertex form, I'm going to write it using function f of x because f of x and y are interchangeable. And that's going to be f of x equals a times x minus h squared plus k. This is called vertex form because h and k represent your vertex. And then the last form is called root form, which I did not leave myself enough room for. So we're going to squeeze her in there. And we're going to write it as y equals a times x minus R1 times x minus R2. I made it squeeze. Nope, that looks terrible. Let me redo. I'm going to rewrite it. I'm going to rewrite it. I believe in myself. Y equals A times x minus R1 times x minus R2. Ta-da! My hand is literally cramping trying to write. Huh? Oh my God, that's so crazy. All right, so now that you have the definition and the characteristics, you should be able to come with examples and non-examples of what a quadratic function is. Okay, so we're going to pause for about 60 seconds to come up with your example and non-examples. For the example and the non-example, I would like for you to create a graph. I can spell graph. I could, I can. It just wasn't working at first. I promise I was trying to make a G. Graph and an equation. And then you can come up with whatever you want, but at least 2 non-examples. And go. All right, so let's talk about my examples. So for a graph, I just know that based on what we read, it has to be a parabola, right? So when I draw my graph, I'm just going to draw it down here. Pretend that that's a parabola, the most curvaceous parabola you've ever seen. Okay. The equation again. So for equation, I'm going to write y equals 3x squared plus 31. Is my highest exponent a 2? Yes. So therefore, this is a quadratic. For my non-example, it could be y equals 3x plus 31. And why is that a non-example? It's linear. It's mx plus b. My highest exponent is a 1. I can draw this guy. Is that an example of a parabola? No, it is not. Okay, a parabola is made up of 1 curve, not of 2 curves. Right? All right. Do we see that? So your examples could be anything as long as you are reiterating that. What the characteristics and definition are. All right. Last, we're on to page 3. Page 3 is our exponential function. Okay. So we have our exponential function. So we're going to draw our third Frayer model, our third and final Frayer model of the day. This is going to be the function that you've probably had the least experience with in Algebra 1. Even though it is supposed to be introduced as a growth and decay model, which I hope at least you saw it as that. Maybe? Does that ring a bell? Growth and decay? No? Yes. So it's growth and decay. Go. Okay, so we're on an exponential function. So for exponential functions, it is our least, oh, I just threw a pin at myself. It is our least talked about probably. You probably just briefly went over it in Algebra 1. However, it is still one of our base functions that we should know. All right, so it is a relationship. Again, I promise I'm going to work on my writing. Between 2 quantities. And again, those quantities are x and y. And this, it has with a new term, a constant ratio. Does anyone know what ratio means? What mathematical operations are you doing when you have a ratio? It's fraction, right? Fractions mean that you are multiplying and dividing something. A lot of times people don't consider that But mathematically, the operations that you're doing when you have a fraction is you're multiplying by something and you are dividing by something. A ratio is a fraction. So there's a constant ratio. And that constant ratio, it's either going to be a growth or a decay. So it's a constant ratio of growth or decay. Okay. You got to be more specific where decay. It's the words decay. DEC, decay. Yeah. It looks like a lot of things. I know.
That was really pretty. It's like a perfect A. Anytime you need to write an A,
I will never be able to create that again. I'll never be able to create that again. Looks like a lot of things, like I said. Okay. All right. So our characteristics that we're going to talk about here. So for an exponential function, we are going to remember that a ratio means what? I think Chloe told us. A ratio is another word for a fraction. Okay. Fraction means that you are multiplying and or dividing. Okay. And so a fraction just means you are multiplying or dividing. That's all ratio is. A ratio is a fraction. So when you have a constant ratio, we're going to define when it's a growth. If you have a growth, that means that your function is rapidly growing. Does that make sense? And that's because you are multiplying. Okay. If you have a decay, that means your function is rapidly declining. And if I'm rapidly declining, that means I am dividing. Does that make sense? And with the fraction, the numerator represents multiplication. The denominator represents division. Did y'all at least learn that at some point in life? The numerator is multiplication. The denominator is division of a fraction. Okay. What it creates here is the new word of the day is asymptotic behavior. I'm going to try to write it over here. Yeah. We have what's called asymptotic behavior. Okay. Asymptotic behavior. That just means that I now have a boundary line. Okay. Which we're going to talk about it more, but you have a boundary. Okay. Boundary. Lastly, our function in standard form is going to be f of x equals a times b to the x. Okay, we're going to do the examples together because I understand that it is a newer concept. So the most common used exponential function in Algebra 1 was, or should have been, f of x equals 2 to the x. Do y'all remember ever seeing that? Maybe. Okay. That should have been the one that was most used. What this means is that every single time you're multiplying by 2. Does that make sense? Well, your base is 2 and you're multiplying it by itself. So keep going, keep going, keep going. So we're going to model that. So we're going to do this as a table and then we'll do it as a graph. So table wise, what this means is you have X and Y. And we're going to have 0, 1, 2, 3, and 4. 2 to the 0 power. Anything to the 0 power. Does anyone remember what that rule is? Huh? 1. Who said that? Oh, perfect. Anything to the 0 power is 1. So 2 to the 0 is going to be 1. Now we're at 2 to the 1. Anything to the 1 power is just going to be its self. Okay? 2 squared is 2 to the third is 8. 2 to the fourth, 16. And notice this is our ratio. Each time we're doing what to get from one y to the next? We're multiplying by 2. Because we're multiplying by 2, this would be an exponential growth. Okay? Because if I'm multiplying, then I am growing. Does that make sense? If I am dividing, I am decaying. Okay? Yeah? Are you with me? Okay. So what we're going to add here is for multiplying. That means that your b value is greater than 1. Notice that our base here is greater than 1. For your decay, your b value is going to be between 0 and 1. Okay, so when I graph this, remember I told you that asymptotic behavior? That asymptotic behavior creates an imaginary boundary line that I cannot cross at 0. That's because this function will never go. It just keeps going and going and going and going and going unless I set a restriction. And I'm going to leave you to create your non-examples, but this is our example of a exponential. Got it? All right.